Welcome to my talk. Thank you for the introduction. And I will talk about the effect of T-stress on fatigue past stability in thin-walled aluminum alloy sheets. So that is my team. So I work at the Institute of Materials Research at the DLR in Cologne in Germany. I'm a PhD student, and we work interdisciplinary with physicists and engineers covering a broad range of topics such as machine learning, for example, data segmentation, and of course, experimental fracture mechanics. So giving you an overview about the topic. So first, an introduction about the load case and the aircraft application, the numerical model that we use to evaluate the crack chip stress state, giving you an overview of the experimental setup that we did, and finishing with the results of the conclusion. So first of all, why do we do that? So in an airplane, in a fuselage structure, it is extremely important to know where a crack initiates and where a crack grows regarding the crack propagation behavior with regards to the speed of the crack. And yeah, it's extremely important to know it with regards to, for example, lifetime estimations or service life intervals. So in an airplane, we have some kind of special load conditions. So we have this fuselage over here, and there is a load case, so-called the internal cabin pressure and the external loads cross the so-called biaxial stress state that can be represented by a so-called cruciform across specimen. So if we compare it to a uniaxial load case, in a cruciform specimen, we also have another stress component, the so-called T-stress that is acting parallel towards crack growth. So while there are some methods to predict the crack path on the mode 1 and mode 2 load in uniaxial load cases, sometimes those predictions don't match with the experimental results. So this is mainly because the T-stress often gets neglected, but it does have an impact on the crack path. So the key question here is, how does the T-stress affect our crack path stability in a biaxial load case? So unfortunately, there are no handbook solutions to get the stress intensity factors in a cruciform specimen. And therefore, we performed a finite elemental simulation with a specimen that represents the actual cruciform specimen of our test. And by varying the load ratio between the axis and the crack length and assuming the crack path to be straight, we could outline the role and the impact that those factors has regarding the stress intensity factors delta T and delta K. So the method that we used is the method that I'm going to introduce now. So we wrote a tool. It's called CrackPy, Crack Analysis Tool in Python. So this is a tool that me and my team, we developed it. It's written in Python, so it is like open source, and it's you can scan the QR code and you try it out. And yeah, the key points in that is that we can, based on either numerical or experimental data and displacement field, we can, for example, use AI and machine learning models to detect the crack tip. And afterwards, we can, for example, calculate the stress intensity factors using the J integral or the interaction integral, for example. So just try it out. And this is a method that we use to determine the stress intensity factors in the numerical and experimental setup. So the microstructure of the material that we use is, as you can see here, it's aluminum alloy 2024 with a thickness of 2 millimeters. So it's kind of thin because the material is cold rolled. And this causes some anisotropic properties within the material, so some kind of texture formation. So it has the two different orientations, namely TL, where the crack grows parallel to the elongated grains, and LT, where the crack grows perpendicular to the elongated grains. So to outline the influence of the microstructure within the material. So the test setup, in the first experiment, we stated the hypothesis: does the crack deflect if it's been applied to a positive T-stress? So therefore, we set up a delta T range based on the assumption of the simulation, and a delta T range in which we significant sub-steps used to increase delta T between negative and both positive values. So in the second experiment, we address the hypothesis: does the magnitude of T-stress causes crack deflection? So therefore, the delta K range remained identical. but we increased delta T to a higher magnitude, that there was only positive T stress. And in total, we performed 4 experiments to outline the influence or the role of the microstructure and the load condition to the crack path. So there you can see our experimental test rig. So we've got like the test rig with 2 servo-hydraulic cylinders on each side. We've got the cruciform specimen in the middle, and we use 2 DIC systems. So the first DIC system is over here. It's a full field, a 3-dimensional DIC system that's capturing the specimen full field. But the other system that we use is 2D high resolution DIC system. So which is like actually a camera with a microscope on it. So the system is being guided by cobot. So how does it work? So the load is applied cyclically and in phase. So that means that on defined points, we stop the machine at maximum and minimum load. And then the 3D DIC system captures an image. So there, here you can see the strain field. So we capture the strain field and the displacement fields. And using the algorithm given in CrackPy, we can detect the crack in situ. That means we already know the crack tip position during the experiment. And then the robot moves forward to the position of the crack tip. And then we capture another image, like a 2-dimensional, actually it's a 2D image, namely a microscopic image. That means that we get a higher resolution, but a smaller image, of course. And this enables us to get a high resolution DIC image that's having a actually higher resolution, capturing more details of it. So coming to the result, on the left hand, you can see the crack path that we can obtain within the 3D DIC field. So like every crack tip has been detected automatically. So this helps us on the one hand to detect the crack path, but also to calculate the stress intensity factors and to the crack propagation behavior and crack propagation rate, the RD and delta K. So on the other hand, the high resolution DIC gives us actually a detailed view of what's happening at the crack tip. So this high resolution data can be used, for example, to capture the plastic zone and to identify like crack growth mechanisms, for example, crack pointing or secondary cracks. So coming back to the initial hypothesis, does positive stress lead to crack deflection? So actually, we can see that for the first experiment, the crack has been subjected to both positive and negative T stress. It depended on the rolling direction. The crack remained like kind of stable. So the crack path remained quite straight. So we also have a good agreement between the experimental and the numerical determined crack tip loads. Remember, the crack has to be assumed to be straight within the simulation. There you can see also that the delta T range significantly increases in stepwise. So for the second experiment, where we subjected a higher magnitude of T stress, one can outline that the crack does deflect. So actually a higher delta T and the higher T stress leads to crack deflection, but the crack deflection depends on the rolling direction. So as you can see here, that the crack in LT orientation, that means where the crack grows perpendicular to the elongated grains, starts to deflect at an earlier point. So actually also the crack deflection causes deviation of the actual crack tip stress rate from the assumed straight crack in the FE analysis, as you can see over here. So coming to the conclusion. So I've shown you that classical fracture mechanic experiments can be enhanced with some methods like legal image correlation. And this enables us to get a deeper insight towards the underlying mechanism of the crack growth. So this is only possible because of actually the higher automatization level. As you can see with the robot, it's moving to the crack tip position during the experiment. And the highly automatic test setup enables cost-efficient fracture mechanic tests with a higher data output that can be the base of data-driven experiments. So regarding the role of the T stress, we have seen that the positive T stress does not necessarily lead to crack deflection, but the tendency of a crack to deflect may be due to an interaction between the microstructure and the magnitude of delta T. So thanks for the attention, and